So far, what we know about this machine learning projects is we know that we need certain data, right? We need to get the data, appropriate data. Then, of course, the data may suffer from the quality issues, right? We need to do some sort of pre-processing, right? And then further, what we can do is some feature engineering part, which are the important features. I can just sort of extract the important features and start feeding it to a sort of model training, right? This is what I will do. So I'm going to split my data into train and test. Training data will be used for training the model. Once the model is trained, you will validate it by testing it on the test data, compare the evaluation metrics. If they are acceptable, you go ahead and deploy the model, and then there is a maintenance. This is what basically the life cycle of a machine learning project is, right? But now the question arises is how do I select the data, right? And this is one method is like holdout method. So there are systematic ways of testing the model on the unseen data, right? To check it out, like how it will perform on the real world situations. So there are ways. One is holdout method, which we have been talking about, right? That you are building a model, let's say, to predict whether a student will get a placement or not. And you have got, let's say, a data of 300 students. And instead of using 300 records for training, you divide it into two independent parts and you say that 2/3 of the students, like 200 students records you will use for training and 100 student records you will use for testing, right? And then the model say learns from the 200 training records and then tested completely on unseen data, which is 100 records, right? And model may be able to, let's say, correctly predict the placement outcomes of 85 out of 100, and then the accuracy becomes 85%, right? So what we're trying to do here is simply dividing the data. Just a minute. I'm dividing the data. If I have 300, 200 will be used for training, 100 will be used for testing. And that's what the holdout method is. So what is the problem? The estimate is pessimistic because only a portion of initial data is used to derive the model. So we are using one portion, right? We are not testing each and every sample, right? Is there a way that we can do better, right? These are the questions which we need an answer for, right? So in the other way, if I put it, what if by chance our test set became unusually easy or unusually difficult, right? Whatever is my training set, the test set is completely different from that. So maybe whatever the model has learned from the training data, training parameters or evaluation metrics may be very good, but when it is tested on a test data, it may not be. So that may give you an unreliable estimate overall. So what should we do? We have some other techniques. How do I divide my data? One is the random subsampling, right? So instead of splitting the ones, we repeat this holdout process, right? Holdout, 2/3, 1/3, right? Multiple times. And this is done randomly. Maybe the first time which I'm getting 200, right? Second time I'll get a different set of 200 records. Third time I'll get another different set of 200 records. So every time it's not the same 200 records I'm doing. I'm repeating it with different. Randomly I'm picking some 200 records, right? Some of them may be same with the last pick. Some of them could be different, right? Only. And what will happen is 5 times I'll train the model. Maybe the first time, let's say the accuracy is 80%. Second time 85%, right? Third time 90%, fourth time 75%, and fifth time let's say 95%. So I'll take the average of all 5 model and say this is my average of all the runs, and this way we can mitigate those things, like if my test training and test data differ significantly. So I'll be able to handle that part. Third thing is data selection techniques, right? We have covered all these things in the last session, but little quickly. So I'm just repeating this portion. Are you able to follow? Yes or no? Quick comment on this. Are you able to follow what I was talking about? Vasu? See, if you're not able to follow, kindly stop me, ask some relevant questions. Otherwise, how we will proceed, right? Some communication has to go. Where you are stuck, you have to stop me, ask. Some effort, some self-motivation should come, right? Otherwise, I mean, it's like a monologue that's largely happening. Okay, now moving ahead, k-fold cross-validation. What happens in k-fold cross-validation, right? So we have covered two as of now. One is holdout, dividing the data, right? Then random subsampling. You do repeat the holdout method multiple times, right? Now in k-fold cross-validation, what you do is you initially partition your data into k mutually exclusive subsets, which are known as the folds of the data. Now, if let's say you have 500 records, right, you might divide into, let's say, 10 subsets, each of size 50. So what you will do is you will give every time, let's say, 9 subsets for training, or we call them as folds, right? 9 folds for training and 1 fold for testing. And how do we repeat this process is, let's say first time, first 9 are given for training. And let's say these are D1, D2, D3, D3 up to D10, right? So first D1 to D9 are used for training and the last 50 are used for testing. Second time what will happen is I'll use D1 to D8 and D10 for training and D9 I will use for testing. Then I'll use D1 to D7 for training, 9 and 10 also for training, and D8 I will keep for testing. And then D7 I will keep for testing, rest all I will use for training. Then after that D6. So I am using 9 folds for the training and 1 fold for the testing, right? So I'm going to train my model multiple times and there will be different accuracies that I will achieve, right? And then I will have to take the average accuracy of the model, and this is more reliable because every data point is going to get a chance to become the test data. First time last 100, then second last 100 records, then third last 100 records are test data, and so on. So model will also get a training, right, for each and every sample, and each and every record will also get a chance to become a training data, and each and every record will also get a chance to become a test data. So there will not be subtotal difference as such, but of course over a period of time these parameters will improve as you have these folds. So 10 is the most popular number. K is equal to 10. You actually make 10 folds of the data and then repeat this process, right? Cross validation. There are two techniques within that. One is leave one out. Leave one out is very simple. It's a special case of k-fold cross validation, where k is the set of initial tuples. The only difference here is you keep one tuple out and rest you will use for training. If let's say you have 100 records, 99 you will use for training, 1 for testing, right? Then maybe uh, second last record then you will use for testing, a rest all for training. So 99th record, then 98th record, 97th record, and so on. So this is leave one out cross validation. So almost all data will be used for training. So but what will happen is, even for 100 records you are training your model 100 times, so it becomes computationally very expensive, right? So because model training is not an easy job, easy in a sense, it's a computational heavy job, because the data that you are dealing with is quite large. So that's another method. Another is stratified cross validation. This is another way of kind of, you can say, selecting the data for training and testing. Now, suppose, let's say my data has, it's a patient data. I know I have 95 healthy patients and 5 are with a particular disease. Now, if I do randomly split the data, what might happen? If I say 70%, 30%, all 70% which I am using for training is, it could come from the healthy patient class, right? And model will never learn that 5% patients which are having certain disease, right? So when I'm picking up a data for training, what will happen is, uh, in every fold which I am going to use, this is also fold with folds, right? Stratified 10-fold cross validation. So in every fold, I will have to ensure I have the same uh, population diversity which I have in the original complete data set. If 95% are healthy patients, 5% are unhealthy patients. So I, in every fold, let's say if I am picking some 100 records in every fold, so 95 should be healthy, 5 should be unhealthy in every fold. It is not like that in every fold I get, okay, in maybe 8 of the folds I am getting all healthy patients, and only in the 9th and 10th fold I am getting unhealthy patients. So that's not a balanced split, right? So whatever is there that exists in the original population, that is what I want to take in stratified cross validation, so as I have a very realistic estimate overall. So this strategy will be even more balanced, right? And then comes the bootstrap thing. We have covered this also in the last session, that you typically choose the training samples with replacement, right? So let's say if you have chosen A, B, C, D, E, right? You randomly select one student, A, let's say, right? And now instead of removing A, you put back A into the record. So A may come twice. Similarly, B may come twice, C may come twice, right? Within the record. So some records may be appearing twice or thrice, right? While some records may not be selected at all, right? So the selected samples which we are using, that forms the training set. The unselected samples, they becomes the test set, right? So this is how it happens. So now there's an interesting thing within this bootstrap. It says that 63.2% of the original tuples will end up in a bootstrap sample, and the remaining 36.8 will form the test data. I mean, this is all probability based, because when the data set becomes too large, the probability calculations actually show that 63.2% records are selected at least once. This you have to repeat it, experiment, right, and then select it, and then check the probability of each, right? Then you will, on an average, you will see 63.2% will get selected and 36.8% will not get selected, and they will become the test data. That's something experimentally we can do. That's all about bootstrap. Right now we are going to start an important topic, ROC curves. We've talked about, if you remember, uh, true positives, right? We've talked about false positives. We've talked about false negatives. We've talked about true negatives. Now, can somebody quickly tell me what these terms are? A quick answer. What are true positives? This is basically related to classification model. We know classification is supervised learning. All of you know what supervised learning is? By now, I hope all of you know what supervised learning is. Yes or no? Okay, you know what is supervised learning, right? So you have a labeled data, you have set of input features, you have an output, right? So you divide your data into train and test, you train your mock classification model, and then you give it test data. Okay, I have the output for the test data, but I will not share the output. I will ask the model to predict. I will only give the input features and let the model predict. Once the model will predict, I will compare it with the actual output if it is matching or not. Right? For a binary classifier, either the class could be yes or no or 1 or 0 or red or green, right? Something like that, when there are two possibilities. So these are the parameters that we are using for binary classifier, right? True positives are the one which, let's say, predicted were also yes by the model and actually were also yes, right? They were positive. Those are the true positives. False positive means falsely labeled as positive. They were actually negative, but model labeled them as positive, so known as false positives. False negative is falsely labeled as negative. They were actually positive, but model labeled them as negative. So these are the wrong predictions by the model. True negatives, they were actually negative, model also predicted negative. So these two, TP and TN, are the correct predictions by the model, while FP and FN are the wrong predictions, right? And basis that, we talked about accuracy, precision, recall, sensitivity, specificity, all those parameters we have talked about in detail. Now, there's another parameter that we, another interesting thing that we cover is ROC curves. ROC curves, they depend on two aspects. One is true positive rate and false positive rate. Right? True positive rate and false positive rate. Okay, if model should perform good, right? We want the model to perform good. Which of these two things should go up? Up means should be have a higher value, and which of these two should have a lower value from your understanding? Yes, quick answer. See, otherwise I'm also not very interested right now. If we are putting an effort, so I am also expecting some effort from your end. At least unmute and speak. That leverage I am giving it to you. True ones should be on the higher side, false ones should be on the lower side, right? Very simple thing. There's no rocket science in that. Whatever the true predictions are there, that should go higher. False prediction should go lower. We're talking about positive thing here, so we will talk in detail about why we are talking about positive aspects, right? Okay, now a little bit of theory about this ROC curves and all, right? So ROC stands for receiver operating characteristics, right? So receiver operating characteristics curve this becomes, right? And let me explain it in a very simple way. Let's say the bank has developed a fraud detection model, which we have been talking about in our sessions quite often. Fraud detection. How many actually fraud cases did we correctly detect? That is the number one questions that the model should be evaluated on. And how many genuine transactions are wrongly marked as a fraud? So TPR we want to predict, FPR we want to predict, right? So TPR is how many fraud cases. Fraud means these were the positive cases, right? Positively fraud cases. How many those are we are able to detect, and how many genuine transactions were labeled as fraud. That is FPR. So now there is a trade-off between these two things, right? If you try to increase one, maybe the other one will sort of go in the other side, right? So I'll let you know what I mean to say by the other side, right? So this is these two, right? How many actual fraud cases did we correctly detect? That is TPR, where I'm talking about true positive rate, and how many genuine transactions were wrongly marked as a fraud? That is what I'm talking about, FPR, right? Now, there's a theory how this ROC curves, from where these ROC curves originated during World War II. What was the challenge was radar operators had a challenge that they need to identify the enemy aircraft using radar signals. But the radar also detected birds and noise, and this created a good amount of possibilities, right? One is true positive, where the radar signal says there is an enemy plane, and there were enemy planes actually, right? And this is a good result, true positive, good outcome. There's a true negative also. Radar operator said there is no plane, and there were actually no planes. This is again correct, and this is a good output, and we didn't waste any resource. False positive. Radar says enemy plane exists, but actually there were none, right? So this is kind of what the army will do. They'll deploy the resources, right? Because radar signal has given no, the enemy plane is coming, but actually it was not. So it's a kind of wastage of resources. So false positives, right, is actually giving us some cost here. If you look at the application, we want to minimize that cost. I want to minimize the FPR, false positive rate. When it comes to false negative, radar operator said there is no plane, but actually there were planes. So this is going to be a very bad outcome. This is dangerous, right? Because the enemy aircraft may come and drop the bombs. They will attack you, right? But because the radar signal says it is false negative, so this is very, very dangerous, right? So from there comes the concept of ROC curves, right? The same idea we are using in fraud detection, some disease prediction, some spam email detections and all, right? So this is what the contingency table is, right? Truth is on this side and predictions are on this side. So TP is which model also predicted yes, and truth is also yes, right? Then model also predicted no, truth is also no, that is TN, right? Truth is yes, but model predicted no, that is false negative. Truth is no, but model predicted as positive is a false positive, right? So our objective is to minimize false negative, false positive, and this true positive and true negative should maximize, right, from a particular model. Now, to understand, of course, ROC, as I talked about, there are two important things that matters. One is true positive rate, and other is a false positive rate, right? So let us look at what is true positive rate. True positive rate is the proportion of positive tuples that are correctly labeled by the model. So let's say, okay, TP is what correctly labeled by the model, right? But what actually Fn is? Fn is falsely labeled as negative, but actually they are positive. So TP divided by, this is what actually model predicted, TP plus Fn, which are falsely labeled also, right? So this is my sensitivity. I want to increase this true positive rate, right? So let's say if there are 100 fraud cases exist, model actually catches 90 of them, then TPR becomes 90%, right? 10 is FN, right? Falsely labeled as negative. So then TPR becomes 90%. Similarly, you have FPR is the portion of negative tuples that are mislabeled as positive. So F false positive divided by false positive plus true negative. They were actually negative but labeled as positive. So this is sort of known as 1 minus specificity, right? Specificity, we covered it in the last session. What do we mean by specificity? So basically, out of all genuine cases, how many are wrongly marked as fraud? False positives. 1,000 genuine transactions exist, 100 are wrongly flagged. So FPR becomes 100 divided by 1,000, so kind of a 10%, right? So now, very, very important aspect. An ROC curve for a given model shows a trade-off between true positive rate and false positive rate. What this particular graph says is, on one side we have true positive rate, on other side we have false positive rate, right? The orange line, if you see, right, I want the true positive rate to be high and false positive rate to be low. So false positive rate is increasing in this side, true positive rate is increasing in this side. So I want to decrease the false positive rate and increase the true positive rate. So which one should be the ideal point? Can somebody tell me? This is going from 0 to 1 here. This is also going from 0 to 1. Which is the ideal point where we say, okay, this is a good model and perfect model, rather, I will say, not a good model. Any idea? Because this is simple mathematics, the interpretation out of this particular graph. Which one do you say is a good model? You want to maximize TPR, you want to minimize FPR. What is the maximum value of TPR? From the graph, what is the maximum value of TPR? I have told you right now. Can somebody quickly comment on this? These are very small things I am asking. People have joined but not contributing. True ones should be higher, false one should be the lowest. That's one of, I think that is already written. So what is it that from the graph, what is the highest value of TPR? What is the scale where from where it is starting? 0. Where it is ending? 1. What is the maximum value of TPR? 1. What is the maximum value of FPR? False positive rate, what is the maximum value? 1. What is the minimum value of FPR? 0. So if I look at an ideal case, I want TPR to be 1 and FPR to be 0. Do you agree to this? I don't want any false positives, right? I want TPR to be as high as possible. Maximum it can be 1, FPR can be 0. So if I look at two dimensional, so don't you think 1 comma 0 is the point of kind of perfect point for a particular model? If I have to judge it from an ROC curve, 1 comma 0, don't you think it's a perfect point for a model? Yes or no? Ideally, yes, right? That's what first we should learn the ideal case. Of course, we cannot achieve that in practical scenarios, but we should learn the ideal case so that we can understand which model will be good, right? When you look at this dotted line, the black one, right? And this is a square. If you look at this area, right? This is 50% of the area, right? This is 50% of the area. So below this 50% is coming, right? Above this also 50% is coming. So this is kind of a random model, this diagonal line. It's a kind of random model. What is happening is you are increasing TPR, you are also increasing FPR, right? We are also increasing FPR. But you look at the blue line, right? Maybe it may behave like this also, this kind of a zigzag line, the blue one. This could be the actual real life model. And as per this diagram, it says ROC curve with area 0.79. So area means area under the curve. This is the mathematical term. You might have covered it in integration, right? Area under the curve, AUC. So area under the curve is 79%. So, but if you look at this, right, this could be a better model than this random model. The reason being that is here we have true positive rate better than the false positive rate. You see here, it is 0.6 and 0.2. If I talk about this particular point, right? 0.6 and again a kind of 0.3 or 0.35, somewhere like that. And if I go here, it is 1 and 0.6. Right? So this may be a better model than this random model, which is 0.55. So if my curve is going more towards this particular point, which is a perfect point, right? That may be considered as a better model because this is actually reducing my FPR and increasing my TPR. Is it making sense? You can please ask a question. If there is any doubt, please unmute yourself and ask. Should I proceed? Okay, I am moving ahead. So for this course, you have to specifically go through every week, right? What was covered and what was not covered. That's time and again I'm repeating. Okay. Now next thing comes is optimality probability threshold. Now let's talk about an algorithm that predict yes or no, let's say email classification problem, which we have discussed earlier, right? You can consider it as spam or not spam, but here the example is a little bit changed. You can see here it's a terrorist email or not, right? The class is yes, non-terrorist email, no. So basically the model is tracking some secret communication among the terrorists, right? So looking at some features, attributes of email, it is classifying it as a terrorist email or not, right? So it is absolutely necessary for the model to identify the terrorist emails correctly. So we want the true positive rate to be high, right? And that is why we choose the sensitivity as a metric to improve this model, because the occurrence of false negatives, negatively labeled as false. Actually, it was a terrorist email, but model labeled it as negative. So it skipped through. And you know, if it is skipped through, it can compromise the security of a nation. So the result is too dangerous. We cannot allow a false negative to happen. We might end up in having few false positive. False alarms are there. Okay, the email was genuine, but it was classified as terrorist email. It is still okay because you will verify it and then you will later on realize no, it was fine, right? Maybe some resources you will have to waste and so on. But can we allow false negatives? That is going to be dangerous, right? If we allow that. Let us say there are two models which have the same sensitivity score, right? Same sensitivity score. Does it mean that two models have equal predictive power? Sensitivity score means the true positive rate. The true positive rate for two models is same. Now, once the true positive rate is same for two models, what will differentiate the two models? How I will say that, okay, model M1 is better than M2 because the TPR is same for both M1 and M2. What other things, what are the other metrics that I should check basis which I will say, okay, M1 is better than M2 or M2 is better than M1? Any thoughts around this? Yes. Do you think the two models have? Yes. I think somebody unmuted. Please comment, right? What will happen? It may go wrong, but we'll understand the concept, right? Does that mean two models have equal predictive power? The answer is also written no, but I'm asking why no. True positive rate for two models, right, is same. Now, where will the difference come? With respect to this example. See, very simple thing is we don't want any false negative, because if they are able to bypass your system, right? Terrorists are able to send an email and they are able to communicate. It can compromise the security. So you have to minimize the false negatives. Which model will have lesser false negatives? That is what we will say, okay, this is fine, right? This is better. That's what it is, right? Simple thing, not very tough. You just have to focus. How many of you have pen and paper handy with you? How many of you are taking notes? See, because of this reason, I think it is taking a lot of time. I don't know. A much more true positive. See, what do we mean by true positive? What do we mean by true positive? Vasu. Yes. What do we mean by true positive? Model predicted correctly. What? True negatives are also what model is predicting correctly. TP is also model predicted correctly. TN is also model predicting correctly. Positive scenarios, right? So when we say model is predicting correctly, then we say overfitting. Overfitting is the case when there are two aspects, right? One is training data, right? Another is testing data. Overfitting will come when you train it and then you have some evaluation metrics here on the training data. All right. And these evaluation metrics are very good, but when you give it to test data, these evaluation metrics, they go down. Go down is not as good as what we got in the training data. There may be little changes, of course, but there's a significant change. Then we call it as an overfitting. The model learns very well the training data, but fail to fit on the test data. That is overfitting. Now, to how I am getting true positives is by testing it on the test data only. Right? How I am getting true positives? By testing it on the test data. If it is able to perform good on the test data, then of course model is good. There's no overfitting, right? Overfit, question of overfitting comes when the data which you have used for training and the data which you are using for testing, either there's a substantial difference between them, that the model parameters learned during training do not fit very well to the testing data. And that's what initially I've covered these techniques also to sort of deal with all these methods. Holdout is very simple thing. Random subsampling, then data selection subsets, creating folds of the data, then cross validation, then stratified cross validation, right? These will combat to what the situation that you are saying, right? Any other questions? How many of you are taking notes? How many of you are taking notes? How many of you have pen and paper handy with you and taking your notes? Quickly write it in the chat box. Either speak or write it in the chat box. Nobody is taking notes. Should I assume that way? Anish? Ali? Are you guys taking notes? Vasu? Sai Dhanush? Only one response I'm getting. I again request you to be a little more serious for the course. If the concepts are not fine, you will not be able to handle the question paper. Always attend with good. That's good, Anish. Whatever the questions that come to your mind, you can raise that also, right? Questions I am asking, you can answer that also, so that I can come to know whether it is going in your mind or not. I'm asking something because I want to know, right? I'm also spending time. You are also there on a weekend. Something good should go in your head. Okay, let me move ahead now. Now, what typically happens is in classification models, right? What we want is most of the algorithms, what we typically want them to do, predict the probability that an observation belongs to class yes, right? They may not give it, okay, this is yes or no. Some of those algorithms will also give you probability. Okay, this is maybe 0.8 probability chance belonging to class yes and 0.2 to no, right? So we need to decide a threshold for these probabilities to classify the observations into one of the two classes, right? So for instance, let's say uh, the model predicts the probability of an email being the terrorist email is 0.75, right? If I set the threshold to 0.8, then what will happen is this 0.75 is less than 0.8. So this model will classify it as a non-terrorist email, right? So I'm setting up the threshold. If it is greater than a certain probability, right? Threshold probability, rather the only the using the word probability, I'll use the term threshold probability. Then we are classifying it as non-terrorist, otherwise terrorist email. Now, if I set the threshold to 0.75, the same email will be classified as the terrorist email. So what we mean to say is, if I'm changing the threshold, it is changing the model outcome. So the performance of the model or the system varies as we change the threshold. So now the question is, how do we decide the threshold, right? That's another thing. So it is all we need to have inputs from the domain experts, right? Maybe if the model is getting used in banking and finance domain, we need a domain expert from there. If it is being used in the retail domain, we need a domain expert from there, right? If it is used in the security, like as the example which is being shown, we need a domain expert there and then say, okay, this is the probability, then we should go. Right? Two models with the same sensitivity rate are not equivalent. We have understood that. Among these two models, wherever the false positive will be better, that will be more reliable model, right? Lower FPR means the better FPR, right? We don't want to waste any resources because false positive will waste certain resources. You are saying, okay, this is a terrorist email, you will send certain, okay, something is going to happen, but actually nothing is going to happen because it was falsely labeled as positive. We don't want to waste any of our investigative resources on non-terrorist emails that were misclassified as terrorist emails, right? So the threshold that we set can help us increase or decrease the TPR. If we choose a very low threshold, more emails will be classified as terrorist emails, right? And we will be able to catch more true positives. But at the same time, we will increase the false positive rates also, right? So there is a trade-off between these two, that, okay, you are about to catch all the true positive, but at the same time, you are increasing the false positives also. So ROC curve actually helps you to figure it out where you should, what should be your true positive rate and what should be your false positive rate, right? Now look at these two diagrams. What they typically help you, okay, so 1D data containing two classes, positive and negative. Any point located at x greater than some t is classified as positive. So there is a negative class, there is a positive class, right? Positive means suspicious email, negative means normal email. And there is some threshold value t that we have kept, that, okay, if it is beyond that, it is a positive, otherwise if it is negative, right? Now, second thing, if you look at this, on one side you have false positive rate, right? And on other side you have true positive rate. This is a random line. You are increasing TPR, you are also increasing FPR. So this is a random model, right? We want to be better than this random models. So this curve, this the red one, is going to be better because it is more towards this point, right? So this is better than this random model. And if I go by this curve, this will be even better than this because the point is more closer to this. So some points, right, where we are getting this TPR, let's say close to 0.8 or 0.9 and FPR 0.2, this is a kind of a good, right, good fit. Any questions? Okay, no questions. So simple fundamentals is, if you lower down the threshold, true positives will increase, but it will also increase the false positives, right? If you keep the higher threshold, of course, there will be fewer emails that will become suspicious. So this reduces the false positives, but risk increasing the false negatives, right? So it's always a trade-off that we want to achieve in an ROC curve, right? So we have to visualize it the way we see on the right graph, right? And then take an appropriate call, where should I fit that, right? Look at this. Again, the same diagram. 0, 0, declare everything is to be negative, right? If this is the point, this says everything is negative. There is no positive class. 1, 1 says everything is positive, this particular point. There's no negative, right? Both are not very practical scenarios. 1, 0 is something that we want. This is an ideal case. Earlier I told you that this point is an ideal point, perfect point, because where true positive rate is 1, false positive is 0. But again, these are all the cases which are not very practical, right? Diagonal line is a random guessing, as I told you, because here 50% lies above, 50% lies below, the kind of a random guess. Below the diagonal line, right? Prediction is opposite to the true class. So if this is true class, this is a negative class, right? So this is simply an interpretation of these different parameters, right? Now look at this, comparing two models, right? If you look at this, this is a dotted line, which is the black one. This one, this is a random guess, right? The same graph. Now you see the red line. And it is initially, you look at this, true positive rate is increasing without increasing the false positive rate. And then beyond this 0.3 value, if you increase the true positive rate, the false positive is also increasing, and so on. If you look at the blue one, right? Initially, if you are increasing the true positive rate, and the false positive rate is also increasing, but at from beyond this point, right? If you are increasing the true positive rate, again, there's a increase in the false positive rate, but it is cutting this particular model. So is which model is better, right? From M1 and M2, given these two curves, which model is better? If I look at this point, right, initially this was doing better, right? And beyond this point, then this I can say is going better, because this has sharply increased the false positive rate beyond this point, but this is still going slowly. Which model is better? So we cannot comment on that, okay, this particular model is better. So no model here is consistently outperforms the other. We cannot say that. If one of the curve would have gone like this, outperforming everybody, then I could have seen this is the best model. But there is an intersection in between. So I cannot say that this M1 is better or M2 is better. But there are certain interpretations, right? What it is saying is M1 is better for small FPR. Which is M1? The red line, right? If false positive rate, I want it to be smaller, right? You see initially. I want the false positive rate to be smaller, right? Then of course M1 is better. M2 is better for larger FPR. So if I talk about M1, let me take an example in medical diagnosis, right? We don't want unnecessary panic among healthy patients. So we don't want the false positive to be high. We want the false positive to be small, because the patient is not having a disease actually, but model says you have it. It will create an unnecessary panic. So in such cases, we will prefer a model which is M1 if I have to choose between M1 and M2, because I want to minimize the false positive, right? Now, when I talk about M2, let me take an example of fraud rate. I'm saying higher false positive rate. This might click you. Why we want to increase the higher false positive rate, right? This might be something that comes to your mind. Why should I do that? Why I want to increase the false positive rate, right? Let's take an example of fraud detection. What might happen is we can tolerate some false positive there. Some false alarm is there. Okay, this particular transaction could be a fraudulent transaction, but actually it is not, right? But what if a fraudulent transaction passes through? That is the major problem. That is the major problem, right? So we don't want a sort of any you here look at it, the TPR is going at a higher rate, right? But there is also false positive, right? There is also false positive. Now beyond this point, you see the TPR is matters, right? So TPR, we want true positive, it should pick up, it should not leave anything, right? It should not leave anything. So we can tolerate a bit of false positive rate because it is not going to cost much in my model, right? While I'm looking at a healthcare system, right, where I don't want to label somebody as you have this particular disease when actually the person do not have, it will create some panic. I don't want that. So then I'll choose M1. The moment I want, okay, I don't want any fraud to happen, I'll go with M2, right? Then I'll go with M2. So area under the curve also decides. Now area under the curve, if I look at this red curve, right? So this is the area from here, right, till complete this area is this. So more the area under the curve, the better the model is, right? So if you take this random line, 50% of the area is under this, right? But it is more than 50%. So obviously it is better than the random line. So if I look at this particular curve, maybe the area could be same as what the other curve is, the red one is, but we have different applications of two different models, right? In one domain, one model could be used, while in other domain, other model could be used, depending on what we can tolerate and what we cannot. I hope it is making sense. It's all conceptual things. There is no one single thumb rule, okay, this will work for in every situation. You have to understand and then think, okay, which model is better. You can expect these kinds of questions in your examinations. Now look at this particular aspect, what it is showing. I was using a one line trade-off between TPR and FPR, because the moment you try to increase TPR, you want to catch all positives. Sometimes it will also falsely label certain things positives, right? So if you look at this particular model, right, TPR is 0.2, FPR is 0, false positive rate is 0, which is falsely labeled as positive. You will look at this, right? Total, how many records are there? 5. But Fn is high, you see. This is Fn, right? So out of 5, which were actually positive, it is able to classify only 1. So 1 by 5 is 0.2, right? But my Fn is also 0. So you look at a false positive rate. Sorry, Fp is also 0. So false positive is 0. Look at the second one, right? Look at the second one, where this is the highest threshold, right? 0.90 is the threshold. If something is greater than 0.90, if the probability of yes is greater than 0.9, then only I'll classify it as a positive, otherwise not. Now I've reduced it to 0.8. So 2 yes, 3 no, right? So I am able to increase my true positive rate, but still my false negatives are, false positives are 0. So that remains at 0. Then I reduce it to 70%. So then I have introduced few false positives. Look at this, which is one record out of 5. Then 0.60, it is 0.6 and 0.2, right? 2 positive rate. So I am able to predict more true positives, right? Then I did 0.55. Then again, I am able to pick more. So if you look at this, right, I am decreasing the threshold, right? I am able to increase my true positive rate, but at the same time, you see this is 0.8, 0.2, now 0.8, 0.4, 0.8, 0.6, 0.8, 0.8, 1.0, 0.8, 1 and 1. So the moment I am decreasing it, right? So uh, true positive rate is increasing, at the same time false positive rate is also increasing. But I want a trade-off. If I have to ask you one point which you have to choose, the best point, which particular point you will choose out of these tuples? Like if I say 1 2 3 4 5 6 8 7 8 9 10, which particular point you will choose? I'm saying, okay, let me give you the false positive should be high. Sorry, the true positive rate should be high and the false positive rate should be low. See, if you don't remember this contingency table, it will be hard to follow. I have spent enough time in the last session on the contingency table. So if you have taken notes somewhere, this will help you. I also asked you, okay, you please paste it in your room where you study, because there are a lot of evaluation metrics which will confuse you. And you don't have books during your mid-semester exam. Look at this point. You have true positive rate as 80%, false positive is 0.2. This will be more closer towards that perfect point, right? So if you look at this particular inner model 0.55, this is giving you the best results, right? Most, I mean, good results overall, better than the others. Look at this, the same thing we've drawn, right? We initially started with, you can say 0.20, 0.40. So this is 0.20 till this point 0.40, and then 0.4, 0.2, this point, then 0.6, 0.2, this particular point, then 0.8, 0.2, this point. You see, it is more closer to this, right? And this is what convex we are saying, this is the best point, right? And then if you look at 0.8, 0.4, 0.8 is here and 0.4 is here. So at this same TPR, we are just increasing the FPR now. 0.8, 0.6, again at the same TPR, we are increasing the FPR. 0.8, 0.8, we have now equal TPR, FPR, right? 1.0 and 0.8, this particular point, and 1 and 1, this particular. So this is the major point, right, where you'll say, okay, this is good enough. So I can, now if I want to decide a particular threshold, right, for a model like this, so I can do that way, that this is what I want. So it depends on the domain. I don't want any false positive, then I will go with a different model, right? Maybe the first two, 1 and 2 will help me out in that. Then I should go with a second choice. But if I can tolerate some amount of false positive, then this is good enough. Best. I want to capture all TPR. False positive is not very resource intensive for me, or then I may go ahead and choose this kind of a model also, right? So it depends on, like, how many resources do I have to see when I'm checking some false positive, one particular false positive, how many resources I have to put, what is the cost incurred in order to check that. So this is very simple comparison between two different models. Uh, Now this part should be very simple. If I ask you which model is better, see the same graph. This is your random thing. This is M2, this is M1. Which is better? The model which is closer to the diagonal line, right? It is less accurate. This is what is mentioned here. Model which is closer to this particular perfect point, right, will be better. So M1 is more closer to this, more away from the diagonal, right? So both conditions are satisfying, right? So M1 looks to be better model than M2. These things you should know now, right? And even the area under the curve, if you see, M1 has a larger area under the curve than M2. I hope it makes sense. This is all about ROC curves, right? I'm moving ahead to another thing, hyperparameters. This term might have been introduced in your lab sessions, right? But it is just one aspect that we am going to cover here, but it will come in more detail as I move to the regression, which is probably maybe I'll touch upon it today a little bit, right? What is gradient descent? What is mini batch? What is regularization constant and all, right? So gradient descent is one algorithm used for maximization or minimization problems. You want to find out minimization, minimum number from a function, or a maximize where the function will have the maximum value, where the function will have the minimum value. For that particular thing, we can use a gradient descent, right? So how do you relate these parameters to, right? Let me take an example of cooking. You are using some electrical appliance, let's say a pressure cooker, right? You want to cook rice in a pressure cooker, which is electrical appliance. Before the cooking starts, right, you would decide certain parameters. What is should be the flame intensity, right? How much temperature should I set? What is the cooking time? What is the water quantity that I should keep in the rice? Now, all of these settings affect the final output, right? Maybe if you say, okay, I would have a higher flame intensity or a higher temperature, you want to do some fast cooking, yes, that can happen, right? You want to go do some slow cooking, you can reduce the flame intensity, and so these are some parameters which actually controls the final output, how if effectively or how fast or how slow the final output is achieved. So on the similar lines, ML algorithms also have settings because you want to either find maximization or minimization, right? These are the kind of problems that do exist within machine learning, right? Or we convert a particular kind of problem into maximization or minimization problems and then apply machine learning on it. So there is a very important parameters learning rate, right? In gradient descent algorithm, how fast my algorithm should learn or reach to a minimum point or a maximum point, right? So that is a learning rate. Now, if it is set too high, right, model will find difficulty in converging. If it is set too low, it will take too much time to reach to a minimum or a maximum, right? So these are hyperparameters for machine learning model, which we have to supply externally. Once we cover gradient descent, it will be more clear. And then number of iterations is also one of the parameters, right? How many iterations you want to run for a model? Whether you want very few iterations, then of course the model may not learn the parameters that effectively and you may end up in underfitting. If you run too many iterations, model may learn very well these parameters on the training data and may end up in overfitting, right? So we have to come up on a middle path. What is the appropriate number of iterations that I should run? That's another hyperparameter, right? Then comes in the batch size. How many records should I process at a time? Should I give 1,000 records, right? Or I should process these 1,000 records one by one or in batches of 100. That's another thing, right? Regularization constant, which helps to prevent some overfitting things, right? We will learn about the regularization constant soon. I think it is a part of your lab sheet one also, regularization parameters. Professor Omshri might have covered it already. Lasso regression and lasso and ridge regression. If I'm not wrong, they introduce certain parameters, lambda and all, to control the weights of the model, right? Don't worry, I will cover it in more detail. Uh, but let us cover first what is MLOps, right? How many of you have heard the term DevOps? Quick answer. How many of you have heard the term DevOps? This is quite common in industry nowadays. So from your understanding, if you know what is DevOps, can you write one line or comment on it by unmuting yourself? What is DevOps? What is DevOps? You're not using it. They work in resource management in my provisioning, maintaining, scaling resources. Exactly, right? So kind of see what earlier used to happen. There's a development team and there is a deployment team, operations team we call it, right? Development team will develop a particular software and then the deployment team takes over and then they'll provision the resources and maintain that particular project over a period of time, right? They have to deploy it on appropriate resources and all. So there was a kind of a gap between the two teams in a traditional software development. What DevOps, when the DevOps came in, it bridges that gap, right? That development and operations, they go hand in hand, right? And this has been quite successful in the industry right now, right? And being practiced by most of the organizations. Now, when it comes to machine learning projects, they also go through a life cycle, right? The life cycle of machine learning project is a little different. So maybe you start with the data collection, then pre-processing, then under pre-processing, if I say, okay, feature engineering is also covered, that's one other part. Then model training, then testing, and then deployment, and then monitoring it. So this is what the typical life cycle of an ML project is. It is in similar lines with the software development, right? The same goes with that. You do some feasibility analysis, requirement analysis, and then you say, okay, we will use this kind of a tech stack. You design it, then you code it, and then after coding, testing team takes over. Once the uh, testing is okay, then you start pass it on to the operations team for deployment and then monitoring, right? Here it is more model training, testing, and so on. Now, when you see these different stages, right, you can assume it as a sort of an assembly line of a factory where multiple steps happen systematically, right? The way you must have seen the cars are assembled, the chassis will move over a belt, and there are different stages a car goes through. One might fit tires, another might fit engine, and other things, right? So at the end, you get your car ready, right? Once that it has cleared the that particular pipeline, right? So we call this as an ML pipeline, machine learning pipeline. If I talk about ML ops, right, it stands for machine learning operations. So what it combines is it combines two aspects. One is development, then other is operation. The way the term DevOps was used, right? So ops for machine learning systems. Now this is development and operations for machine learning system. That is what ML ops is. So it is very similar to the DevOps principle, which the industries have already practiced, right? So basically in DevOps, you have a CI/CD pipelines, right? Continuous development, continuous integration, and so on. On the similar lines, we have a continuous management of machine learning models as well. For instance, let's say there's a very popular organization, Netflix, right? All of you might have used that also. They generally give certain recommendations. They have built a recommendation model. Initially, it works well, but after 6 months down the line, maybe the user preferences change. The older recommendations may become irrelevant because of 6 months down the line, the same model may not work. The older recommendations will become irrelevant. So what the model needs now? Model needs monitoring, retraining, redeployment, right? So if this has to be done manually, now again we want to retrain and again bring some data scientist people, right? They'll collect the data, they will feed it, they will tune the parameters and then deploy. Once the test, then again the testing will be done. The newer model now should be better than the older model, and once it is the that accuracy or the other parameters are acceptable, you redeploy it. But it will take a lot of time, right? Because every time this 6 months down the line things are changing again, you have to redo the things, right? In order to kind of fasten this process, ML ops came in. So the goal is to automate and continuously manage this complete ML lifecycle, including that monitoring and retraining part, which I'm saying, right? This has to be looked into. So this is all about, I mean, these lines which are written here, right? This is all what I've spoken. So automation and monitoring all steps of ML system construction, including integration, testing, releasing, deployment, and infrastructure management. So all this has to be included within ML ops, right? This is all a small fraction of ML real world system, right? It is composed of these things. You can see data collection is there, data verification is there, feature engineering is there, process management, metadata management, model analysis, resource management. So all this is whole ecosystem of ML system components, right? Now, in real world systems, what typically happens is machine learning code, right? What is the center part which you are looking at? Coding is a very small portion of this total system. Majority of the effort goes in sort of the pre-processing part, collection, cleaning, validation, right? So then if I talk about deployment, majority of things will go into infrastructure, monitoring, right? Model retraining. So as beginners, you may think it's all about sort of just doing a code and we are done with the model. That's not the case, right? It's more than that, right? Because it's similar to DevOps, right? You prepare a design first and then start the coding. Of course, coding is considered as a major activity there, but it's not that activity which will consume that, okay, 90% of the time. Similar lines, ML coding is not going to consume much time, while the other things around ML code is going to consume the majority of the time. If I talk about industry, right, they say if often 80 to 90% effort goes into data and operations, while actual model building is only a very small component. And this is one reason why deploying ML systems in production is much more difficult than training a model in a typical Jupyter notebook. So this is DevOps versus ML ops. We've already talked about what DevOps is, right? So rather than now traditional software engineering, organization followed DevOps practices, right? The main goals are faster development cycles, faster deployment, right? Then reliable software releases, and two important key concepts under DevOps comes is continuous integration, continuous delivery, right? ML system again is a software system. Similar practices apply to reliably build and operate at scale. But there are some differences like team skills, right? Team skills in ML, right? Largely they should focus on EDA part, exploratory data analysis, which we've talked about, right? Pre-processing, getting to know your data better, what are the correlations that exist, how many are the missing values, how to deal with those missing values. So those exploratory data analysis should be done. What is the mean of a particular column? What is the mode? What is the standard deviation, variance, and all those things that help us to take certain decisions, right? Second skill that they should have is model development and then experimentation. When it comes to development, then if I talk about the development in DevOps, right, it's largely about writing a code. When it comes to development in machine learning, it's largely experimental in nature. You need to track, okay, you'll do certain experiments, what worked, what didn't work out, right? Uh, then you want to reuse the code maximum time, right? That is something which I can say common across both, but in development of a machine learning model, the most important is experiential nature, right? You should know certain mathematics stats also. Testing. One part of testing is in development is that, okay, what you are doing some functional testing and all, but in machine learning, you also need to do some data validation. Then after the model is ready, then you do testing of the model, how well it is performing, right? And then you do the model validations also, right? So these are the things which are little different from DevOps, right? I'm not saying these are the completely different things, but on the similar, because the development is something different. Testing is little more challenging, right? It's not simply that I'll A/B testing kind of a thing that we follow in software development. Testing at different levels. The data that is coming to me, I need to validate the data. I need to check how many are the missing values and other things. So there are steps that I need to do differently. So if data changes later on 6 months down the line, right, I should not perform all the steps. Rather, I can do certain orchestration of this particular machine learning project, and this should automatically happen. So if you look at the deployment part, right, it's a multi-step pipeline to automatically retrain and deploy the model. It's not a simple thing, right? So this adds complexity, and you need automation before you deploy, right? And you need to train and validate new models before you deploy it, because you will say, okay, we want retraining. After retraining, you need to check whether this has improved over the previous model or not. If not, why you will deploy it? Earlier model was doing well, why should I retrain and then come up with a model which is not good in terms of if I talk about the evaluation metrics, right? Whatever it is intended to do, it is not improving. So why should I deploy it, right? Next is production. ML models can have reduced performance due to constantly evolving data profiles. So you need to track the statistics of the data, monitor online performance. Model need to send notifications, roll back suboptimal values. These are the challenges within the production environment. Because see, the data changes continuously. If you have trained certain model in 2023, right? By 2026, maybe let's say if you have trained a model to detect frauds, fraudsters may use now a different mechanism to make frauds, right? The trained model may not be able to detect them well. So the older model will become less effective because there is a data drift, there's a data profile change in detection of frauds. So how will you handle that? Again, you need to retrain the model, right? So for that, you need a pipeline there. So you need to monitor data statistics, you need to monitor the model performance. And when you see the model performance drops below the acceptable limits, then you may say, okay, I want to retrain the model, roll back to the older stable model, trigger alerts, right? This introduces uh, to new concepts like continuous training, right? It's a new property unique to ML system that is concerned with automatically retraining the models in the production and serving the models, right? Kind of CI/CD you use for software development, right? This is what retraining parts that you will use for MLOps. So this is a traditional way of performing ML things, right? typically what you do is you have data pre-processing, model training, validation, and deployment. These are the 4 steps that you have. If you try to do it manually, right? You trained a recommendation model, let's say in generally, in let's say 6 months before you have trained a model. Now, it may be possible that you want to deploy a little different model now, right? So what will happen? Your data for which you've trained and what you are now in the production, right? They may become inconsistent. They may become inconsistent, and this particular thing is known as this training serving skew. So it is basically what I'm trying to say is manual, script driven, and there are certain interactive processes. There's a disconnection between ML and operations and possibly leading to training serving skew. So simple words, what do we mean by training serving skew is what a model learned during training differs from the real production conditions actually, right? That's what a training serving skew is there. And when this arises, right, the model will no longer be that much effective. And there are infrequent release iterations if you do manually, no CI/CD, active performance monitoring, deploy a trained model as a predictive service, and deployment process is concerned with only deploying the trained model as a prediction service. Right, that's all kind of you can deploy it as a microservice with a REST API and give it a call whenever required, right? So that was the thing in manual. But when you do it with MLOps, right? There are 2 levels of MLOps. One is level 1, which focuses more on continuous training by automating the ML pipeline. So instead of manually retraining the model, automation is introduced, and this step is known as continuous training. Now, let's talk about a fraud detection model. Fraud detection model, let's say it gets a fresh transaction data every week. Every week they are getting. So I'm not going to manually train the model every week, right? I should have a pipeline that should automatically collect the new data, validates the data, retrain the model, test the model, deploy the updated model, and this is what is going to improve the efficiency over the long term. If I have to manually do it, then that's another challenge. And there is always a gap between this operations and machine learning, and then it will come back, and then you will send it to operations, and then every week you cannot do it. But the moment you have built a pipeline, retraining will automatically happen. Things are set up, pipeline is set up, things will automatically achieve. Level 1 MLOps also includes automated data validation as well, right? It checks whether the incoming data is valid. It also do the model validation automatically. It checks whether the retrained model is actually good enough, right? Because if it is not better than the previous one, why should I deploy it? And includes the pipeline triggers. Pipeline trigger means when to retrain the model. So there are triggers with it. When the, let's say, prediction performance drops below a certain threshold, I need retraining. Automatically retrain a model when certain conditions are met, right? So you are targeting accuracy of, let's say, 90%. The time it is above 90%, you will not do retraining. The moment it goes below 90%, you do retraining. Right? So once that pipeline is deployed, the things will be captured automatically, right? Data and model validation, I already told you, right? What do we mean by data validation and what do we mean by model validation? So before retraining a model, you need to check, is the incoming data trustworthy, right? Suppose there were customer age values between 18 to 70 earlier. Now the new data comes in, there is one negative age with a negative value minus 500. Of course, there is something wrong with the data. This requires a validation, right? So another could be data value skews, data schema skews, right? So data value skews means, let's say, if I'm dealing with financial data, there's a loan amount coming in. Average loan amount coming is 2 lakhs. Suddenly it changes to 10 lakhs now, right? This is a major indicate that the businesses has changed, right? Or there is some data issue. So pipeline may retrain a model. Schema means there are some new attributes coming in, right? Suppose there are certain attributes, right? Age, salary, experience that I'm capturing. Let's say one of these column disappears or some new unexpected feature comes in. Then the downstream training may fail because pipeline may stop automatically until this issue is fixed, right? Because whatever the data is expected, that is not coming. If that is not there, of course, I cannot go ahead with that, right? So these are all something that we need to validate first before retraining a model. Is my schema matching? Is the values are in line with what we were earlier receiving, right? Is there any other sort of data which is inaccurate? So all these things we need to do, right? Kind of a pre-processing before you retrain a model. Now, after retraining, you need to do the model validation. Is the new model actually better? The older production accuracy was, let's say, 95%. The newer production accuracy is 85%. Should we deploy it? The answer is no, because my model has gone worse than the earlier model. I should not do that, right? So data validation and model validation are two important aspects, and we need to check other evaluation metrics. I'm only talking about accuracy as of now, but it could be precision, recall, sensitivity, F1 score, whatever is important for our model, I can choose that. The new model must outperform the existing model, only then we should deploy. Another thing that happens is the last point, which undergo online model validation, right? What happens is sometimes these companies, they test new models on a very small group first. It's very similar to A/B testing setup, right? And we call it all as there's a new term given to it as a canary deployment, right? They want to test it on a very small group first. How does it performs as such? They call it as a canary deployment. And if it performs well, they can give it to others as well, right? Now, when it comes to level 2 CI/CD pipeline automation, it's a fully automated ML ops. So there is a rapid experimentation that gets involved in it. You can quickly try new features, new algorithms, new hyperparameters. So that training portion actually gets more I mean, the experimentation which data scientists want to do and say, okay, these features are good with the model, or this algorithm I'll stay with these hyperparameters, right? So that rapid experimentation, what it facilitates. And of course, building a pipeline system will automatically do it, test it, deploy it, right? And there's no heavy manual effort involved. And this kind of speeds up the deployment and training process as such, right? These are the stages: development and experimentation. Iteratively try new ML algorithms and modeling. The output of the source of the ML pipeline steps are then pushed to the source repository, which I was talking about. These are the features I'll use. I'll build a model. What is the what are the evaluation metrics I'm getting? I'll use another set of features and see. I'll change the hyperparameters and see. So all this is experimentation, right? I will try, let's say, 3 different models. I'll try decision tree model. I'll try rule-based model. I'll try random forest. I'll try XGBoost, right? I'll try it with different features and what suits me, right? Then continuous integration, right? Pipeline continuous integration. What it typically does, the new code, right, uh, is automatically built and tested in this continuous integration. So this will include running various tests and checking the components. So it will give you certain packages, executable and artifacts, ready to use ML packages, right, for continuous integration. Continuous delivery. Delivery is artifacts are deployed into the targeted environment. Models are automatically retrained, triggered by the time schedule or by the data change, right? And this is also a complete automation, right? Then comes monitoring. Serve the trained model as a prediction service for the predictor. So this is continuous delivery, right? Retraining, everything happening continuously. Monitoring collects the statistics on the model performance based on the live data, and the output is a trigger to execute the pipeline or to execute a new experiment cycle. So basically, you are monitoring the output in the production environment. If the performance degrades, you want to trigger, right? And you want to do retraining, it will automatically do that. So you have to set up this pipeline. And once you have tested, okay, this is the parameters I want to stick to, your job is done, right? Data gets changed, mod pipeline will detect and automatically start retraining. Performance degrades, another trigger, pipeline will get to know, okay, this model performance has gone down, so I need to trigger retraining. So now you need not to worry about all such aspects, right? So you have built a CI/CD MLOps system by developing these automated pipelines, and now the things will move very fast. So the things that change from level 1 to level 2 is largely uh, trying out different models, experimentation, right, which you can do on the fly, which was kind of not very much possible when within the level 1, right? There is a testing that you will do, and then pipeline deployment will happen, right? But here you see continuous integration, build, test, package, pipeline components, right? Orchestration, experimented. So this is some automation within the experimentations also, right? Orchestration means repeating and the same steps time and again. And orchestration tools are available. Maybe some of you might have used them orchestration tool. It's not only within machine learning and all. Maybe if you are building some big data pipelines, you can use some orchestration tool. Oozie is one of them. Largely theoretical, but we need to understand, right? What is MLOps? So these are the different stages. You have a source code, you package it, pipeline, continuous integration, then a delivery, automated pipeline, and then the trained model, and then prediction service, and then monitoring, right? These are the stages of automated ML pipeline. So continuous integration, continuous delivery, these are the two important components of MLOps. So it's not only about the code, it also includes testing new features, feature engineering testing. If the categorical data is encoded correctly, prediction quality may suffer. So all these things are considered, right? So you need to test for the training convergence, right? You need to test it for NAN value testing. These are all the conditions that may occur. NAN values due to dividing by 0 or manipulating small or larger values. Testing that each component in the pipeline produces the expected artifact. Testing the integration between the pipeline components. So continuous integration checks all these automatically. Delivery, deliver the new pipeline implementations to the target environment. Prediction services of the newly trained model. rapid and reliable continuous delivery of the pipeline and models, right? Now, what they are checking is testing the prediction service by calling the API, testing the prediction service performance. They are going to check the throughput, latency, because when you deploy a model, you have to check multiple things. It does not mean, okay, my model is working well and I can simply deploy it on any part of the infrastructure. I need to check what is the throughput, what is the latency, is it with the reasonable expectancy or not? Because ultimately it should add a business value to me, right? Validating, either go for retraining, batch prediction, verifying that model meet the predictive performance targets or not. So it's all about delivery portion now. Integration is one aspect, delivery is another aspect, right? And there are cloud vendors which provide MLOps frameworks to you directly, right? If you want to know more about them, there's a link given, right? So Amazon AWS MLOps is one framework. Microsoft Azure MLOps is another framework, right? Google also provides Kubeflow and Cloud-Built, right? Sorry, not Kuber, it's Kubeflow. So these are from different service vendors. They already have this framework ready, and this framework helps you to automate all these training, deployment, and monitoring. Add that to at scale, right? I want to scale a model. I need to build a pipeline for that. Right? So we started with methods of evaluation. We talked about various methods of evaluation: holdout method, random sampling method, stratified sampling, then bootstrap. Then we looked into ROC curves in details, a bit about hyperparameters, right? And then largely MLOps versus DevOps, right? So still we have some time. Let me start the regression part. Because though we have already touched upon some of these things earlier, but now we will see mathematically. So be ready for a session tomorrow, right? I will cover this regression in more detail tomorrow. We will actually learn now the maths behind the regression, right? How to solve it. I've been talking about model learning a model. What do we mean by learning a model? That's what we will see. What is a regression problem? Any example of regression? There are two kinds of predictions that we studied, right? One is classification, another is regression, if you remember. Classification largely talks about whether a particular record belongs to class X or class Y, right? Whether the person will buy a computer or not buy, whether a person will do a fraud or not fraud, right? Whether this is a genuine transaction or a fraudulent transaction. Regression is more about predicting a continuous variable. I want to predict the house price. I want to predict the stock price, right? I want to forecast the sales. This is largely a real value that I'm going to predict. This is a regression problem, right? So these are the examples that includes, right, predicting weight from gender, height, and age. These are my input features, right? And weight is my output that I want to predict. But the data that I will use for training, initially that these parameters will be given as an input and this will be given as an output. So model will, the model training will learn a model out of it. Some parameters, weights it will learn. And once it has done that, right, I can then test it using the test data. If the accuracy is fine, or not only the accuracy, I would say that there's another method used is RMSE, root mean square error, for regression. We have covered this also, root mean square error, or R square value. If you have attended the lab session, it might have been covered, R square or mean absolute error, right? That is what we are more interested in. We want to minimize these, right? R square should be close to 1. The values lies between 0 to 1. So minimum RMSE, minimize MAE, those models will be good, right? Predict Google stock price today from Google, Yahoo, MSFT prices yesterday, right? Predict each pixel intensity in robots, current camera image. So all these are regression problems basically, right? How do we now? What are the important parameters that we need to learn? One is correlation. Correlation is something how the two attribute values are related. For example, number of self-study hours you give, right, and the results that you achieve in a course, right? Maybe they are highly correlated. More self-study hours you give, better the output you will, better the score that you will have, right? So there is a strong correlation. If you increase the study hours, it will increase the scores. That is a positive correlation, right? Now, if you sleep more, maybe the performance may go down. If you say, okay, I sleep for 15 hours a day, and the performance will go down. So these are negatively correlated things, right? So similarly, if I talk about with increase in height, the weight increases. So there's a positive correlation, right? So correlation can be positive or negative. This is the formula to calculate the correlation value. This something is the covariance divided by standard deviation of x, standard deviation of y. X and y are the two attributes for which I am calculating the correlation. This is a formula for covariance, right? You subtract from each observation the mean of the value, each observation the mean of the second, right? And divide it by n minus, do a summation of the product of these and then divide it by n minus 1. This is covariance. Standard deviation Sx is calculated as this, right? 1 upon n minus 1 from k is equal to 1 to n, xk minus x bar square. So this is standard deviation of y. These are all statistical formulas. You might have covered it in your probability and statistics course also, right? So x bar and y bar are nothing but the means. This is some simple formula. Now look at this diagram. On one side you might have a y, on other side you have x. Now what is happening is as you are increasing x, right, y is decreasing. The flow is towards this side. So there is a negative correlation. One is the direction, the sign indicates the direction, right? So this is negative. Negative means if you increase one, the other one decreases. How strong is the correlation is given by the magnitude of. -1 means very strong, right? Now, if you look at this, the direction is still this, but the magnitude has little reduced. So little correlation value is little reduced. Look at this. Again, the direction is this. For all negative values, you see the direction is this only. 0, you see this is a random thing, right? You cannot say this. I will say this also, right? So that's why 0. No correlation. The two variables are not related at all. The moment you start seeing a positive trend, it is more in line with this, you more in line with this, you look at this, right? Perfect correlations, -1 and 1. Why this is important? To understand how a particular input feature impacts the output, right? I have some set of input features, right? Maybe the house, size of a house, and outcome is a price. How these two are related? That's important to understand, right? Maybe number of bedrooms is another input feature, right? So how this is related to the price? These are important aspects to understand. Now, in order to identify or not identify, I would say in order to figure it out, the regression thing, right? I can use a closed form equation that directly computes the model parameters, right? Now, when I'm fitting a straight line is normally theta 0 plus theta 1x. That's a simple linear regression model, right? When you have one input feature. So that's a straight line I'm trying to fit, theta 0 plus theta 1x. When I'm using this, just remember the name as of now, closed form equation. I am simply computing the model parameter that best fit the model to the training set, right? Then another thing is an iterative approach, which is known as gradient descent approach, right? It gradually tweaks the model parameter to minimize the cost function. We will learn both of them slowly. Tomorrow it will happen, right? It's already 11 by now. My humble request is I cannot repeat most of the things. The syllabus is huge, right? We want to give you the flavor of the different approaches within machine learning. Please do revise something, right? Whenever you come to the next session. Now, whatever we have covered about regression so far, my humble request is you read it today. Tomorrow I will have a session from maybe around 11:30 to around 1:30. I look forward to your participation. How many of you are ready to attend? How many of you will attend? May I have some response in the chat box, please? Hello? Are you finding this course difficult? Can you please respond? It is not listed in the calendar. Yes, I will post it. I will write to the operations team and they will schedule it and then I'll post it. Right? I'm telling you upfront right now that tomorrow it will be there around 11:30. In the first half we will have. I'm not keeping it at 9. I know people are joining late at around 9, 9:30. So I'll keep it little late so that you can wake up before I start the session. Are you guys okay with this? Something you should respond, right? Hello. Okay. Are you finding it too difficult? You will find it too difficult if you don't remember the concepts.